Ever wondered how engineers design planes that can fly efficiently in every possible condition? It's a huge challenge because aircraft performance depends on complex airflows that are hard to predict. Today, we're diving into a cutting-edge solution that blends two types of data, computer simulations and real-world measurements, using a clever trick called transfer learning. Let's break it down. First, let's talk about the problem. When designing an airplane, engineers use two main tools: computational fluid dynamics, CFD, simulations, which create detailed virtual models of airflow, and experimental measurements, like wind tunnel tests or sensor data from real flights. But here's the catch. CFD data is super detailed but computationally expensive, while measurements are more accurate but sparse. Think of it like trying to map a city. CFD is a high-resolution satellite image, but measurements are just a few GPS points. How do you combine them effectively? Traditionally, scientists have used a technique called proper orthogonal decomposition, POD, to fuse these datasets. It's a linear method that works well for simple cases, like steady, predictable flows. But when things get complicated, like shockwaves or turbulence, POD starts to fail. It's like trying to draw a mountain range with a ruler. It just can't capture the jagged edges. This research flips the script. Instead of linear methods, they're using neural networks, AI models that learn patterns from data. The key innovation: transfer learning. Here's how it works. First, the neural network is trained on CFD data to recognize complex airflow patterns, like where shocks form or how air separates from a wing. Then, it's fine-tuned using real measurements to correct for any discrepancies. It's like teaching a student with a textbook, and then giving them a few real-world examples to sharpen their skills. The network they used is a multilayer perceptron, a type of AI that's great at handling arbitrary data. Unlike older methods, it doesn't need measurements and simulations to match in resolution. You can input things like the plane's speed, Mach number, or angle of attack, and the network predicts pressure distributions across the entire wing, even in areas where you don't have data. It's like having a crystal ball for airflow. Why does this matter? Let's get technical. The researchers tested their approach on the NASA Common Research Model, a standard in aerospace engineering. They compared their neural network to traditional GAPI-POD, a method that fills in missing data using patterns from simulations. The results: the neural network outperformed GAPI-POD in accuracy, especially in tricky scenarios like transonic flow, where shockwaves create sudden, complex changes. GAPI-POD struggled with these gaps, but the AI adapted seamlessly. They measured accuracy using root mean squared error, RMSE, a metric that quantifies prediction error. For subsonic cases, slow, smooth airflow, the neural networks outperformed GAPI-POD by a factor of 4. In transonic scenarios, the improvement was smaller but still significant. And here's the kicker. The network didn't just match the data it was trained on, it generalized to new conditions, like higher speeds or different angles of attack. To prove their method works, the team tested it on real wind tunnel data. The neural networks nailed predictions where GAPI-POD fell flat, especially when dealing with those tricky shocks. This means engineers can now create more accurate models with less data, cutting down on simulation time and experimental costs. So what's next? The researchers suggest this approach could be even better with more advanced neural networks, like ones that account for uncertainty in measurements. But already, this work shows how AI can turn scattered data into a cohesive, reliable picture, opening the door to smarter, safer aerospace designs. Thanks for watching. If you want to see how this tech applies to real-world projects, hit that like button and subscribe for more deep dives into cutting-edge science. Until next time, stay curious.